Great. So my name is Brandon Panos. I'm from South Africa originally, and I did a master's in theoretical physics there, and then wanted to get into machine learning, and a post opened up in Switzerland with the study of solar flares and machine learning. So I jumped into that, I got accepted, and I'm just coming off of finishing my PhD a month ago. And this talk will be my last hurdle to a 2-week holiday. So I'm looking forward to this. But yeah, so in this session, I'm just going to present what I do and then the data. And then we're going to dive into some Jupyter notebooks. And I think a message was sent to everybody regarding how to install all the dependencies and so on. So if you have any problems with that, just raise your hand and we'll get to you. So one last thing, I'm part of a group now in Geneva with Lucia Kleint and Jonas, and we study solar flares as well as stellar flares using machine learning. We're affiliated with a machine learning group in Geneva. So just for some context, this is the sun. I'm sure you're familiar with it. And in the lower left, there's the size of the Earth, just for some context, not the position, which you will see is important now. And at some point, the sun can erupt and expel a huge amount of material and plasma into space. So the question is, what powers these events? And they are, in fact, the most significant and powerful events in our solar system. And ordinarily, the solar disk is so bright that you can't see the outer atmosphere where the action is happening. But when there's an eclipse, it offers a great opportunity to take a look at what's happening in the atmosphere. And we see that the sun's atmosphere is riddled with magnetic fields. And this is what provides the energy for solar flares. So what happens is this is magnetic fields. And what happens is that these fields become tense and can snap like a rubber band. And this releases energy, which is used to accelerate charged particles away from and into the surface of the sun. And when these particles hit the surface of the sun, they slow down and emit radiation, and they heat up this material and it expands back into the atmosphere. And we basically use satellites to record all of this information and try to decryptify it and figure out what the physics is. So here's a video of a flare occurring, and here's the magnetic fields snap in a process called reconnection. And you can see all of this superheated material in these loops. So this is what we study. And the question is, why are we using machine learning on this data? And the first answer would be, over the years, the heliophysics data sets have become increasingly swollen. So the instrument that I used for my PhD is IRIS. It was launched in 2013. And it has since accumulated 20 terabytes of data. Estimator, the Solar Dynamic Observatory, was launched in 2010, and it's actually accumulated 12 petabytes of data. And then DCAST, which is just finished construction, will really outclass anything that's come before it. And we're going to get too much data that we can't actually handle it. So it's become impractical for scientists to actually wade through this data and find the interesting parts to analyze. So what the field needs at this point is a set of robust, smart algorithms that can operate like humans in the space and deliver to us the important, interesting aspects of the data. And secondly, it's not very common to do multi-flare studies, and machine learning has allowed us to perform large statistical studies over many samples of flares. So these are the two motivations to use machine learning. So going back to this satellite on the left over here, this is IRIS. This is the data we'll be looking at today. over here, Iris is looking at a solar eruption. And what you'll notice is that it, unlike SDO that sees the entire solar disk, Iris sees only a small window, but it sees this in high resolution. And you see this flickering line over here. This is a spectrograph, and it's actually collecting atomic data called spectra. Okay, if we look at the data that Iris is producing when it sees a flare, it produces image data, which you can see on the left over here. This is a solar flare occurring. And then all of this atomic data from atomic transitions called lines basically start dancing when a flare occurs. And these signals are what encode the physics of the solar atmosphere. So this is what we're principally interested in studying. And most of this tutorial will be focused on the emission from the magnesium-2 atoms. And what happens is we collect these spectra from a huge amount of flares, and we end up with millions and millions of spectra to analyze. And if you're a human, this is an impossible task to do by hand. So this is where machine learning comes in. I'm sure you've heard a lot about machine learning so far, so I'll make this brief. But basically, machine learning tries to teach a computer how to generalize and think more like a human when novel things come its way. So ordinarily, a computer is very good at well-defined tasks, but as soon as you change some of these parameters, it will fail dismally. And what you see in front of you here is a sample of the Mns Data Set. This is the standard data set for testing machine learning algorithms. And it consists of, I think, 60,000 hand annotated digits, which can take on values from 0 to 9. And what's interesting about this data set is if you look at one number, like 1, or if you look at all the ones, they all differ in some aspects, style, slant, thickness, and so on. And we basically want to allow a computer to program itself so that when something new comes its way, it can actually tell you whether this is a 1 or 9 or 0. So classical machine learning is divided into 2 categories. There's supervised machine learning and unsupervised machine learning. So in the supervised category, we have both the data, in this instance, an image, as well as the truth value, which is generally labeled by Y. And that is that this image that you see on the left is a 0. So what we do over here is we feed images to a network called a neural network. This sets off a cascade of activity down these connections. And then the network lights up one of these 10 boxes in the background, which signifies what number the computer thinks it's seeing. And because we know the truth values, we have the Ys for supervised, we can compare it with the actual value. And if there's a mistake, we can propagate these errors back through the network and readjust the neurons until the performance increases. And in the beginning, this network's doing very badly, just guessing. And in the end, it's making human-type decisions on new data. But it's not very often that our data sets are labeled. So you'll see that unsupervised learning actually just has the data. And this is where all the action really is, because like I mentioned, we don't have labels for real life data. So in this category, you see over here an image of thousands of MNIST numbers from the data set. And the algorithms over here automatically find structure within the data set with no instructions. And what you're seeing over here is an algorithm called t-SNE, and it's grouping all of the numbers into the respective categories automatically. So all the 2s together, all the 3s together, and so on. So there's been a lot of work in machine learning recently. It's exploded. And what we do is we take this, all the methods, but instead of using this artificial Mns data set, we substitute data from the sun. And now we have all of this cutting edge statistical methodologies to tackle unanswered questions in our field. Okay, so our tutorial session today. Like I said, you should have received an email which will tell you how to set up the virtual environments and pull the notebooks off of GitHub. I hope this is working for you. I hope you did it. And if you found it difficult to download the full iris observation, don't worry, because it's not a vital part of these notebooks. But it'd be great if you had everything, then you could code along with me. There's also a photo in the .pix file that shows you what your directory structure should look like. And it should be in this format. Otherwise, some of the parts will be incorrect in the notebooks. You can either make sure it matches this or just change the parts in the notebook. As for the data that we're going to see, we've got this full iris observation. It's 9 GB. I don't blame you if you didn't have the time. But this includes all of the images, the spectra from different spectral lines, and all the headers, the entire observation. And then the data we'll be using most often is a sample of magnesium spectra, so the magnesium line from a flare, as you can see in orange over here, and from the quiet sun. So very much like the MNIST, instead of having ones and zeros, we're having flare spectra and quiet sun spectra where there's no flare. And we want to see whether we can tell between these two using machine learning. Furthermore, if we zoom into one of these spectra, we look at the object that we're studying, we see that it's quite complicated. And it's got a number of features that we put into a dictionary. So for instance, we've got something called the triplet emission, which is how high the emission is over here. We've got the intensity of these lines. We've got what the sum is of this continuum emission in the middle, and so on. So you'll find this in the notebooks. I've created 4 notebooks for us. I'm not sure whether we're going to finish them all. And I think even if we don't, they should be general enough that you can actually start feeding in your own data and playing around with it. So it's not vital that we finish this because I've also posted the solutions in the Git repository. But okay, for our first notebook, we're going to be looking at clustering techniques, which finds the data in the structure automatically. Then we're going to look at dimensionality reduction, where we go from a high dimension and try to preserve the topological properties whilst going to a lower dimension so that we can actually visualize the data. This is the Teesney example that we saw earlier. So we'll actually get to play with not numbers, but iris data using Teesney. And then I will visit a really neat algorithm for detecting outliers called isolation forests. And this is just a fantastically clever algorithm that I think everybody should equip themselves with. And then one of my favorite topics is mutual information. This is if you think of the covariance, mutual information is covariance on steroids. It picks up all the dependencies, and there's a little neat machine that we have here that can be adapted to any data set and is really lightweight and can calculate this quantity for you. So,
Brandon, could I ask a question?
Yeah.
So you mentioned during the previous slide that you talk about preserving topology. That sounds like a pretty serious thing that's going on. I wonder if you could give us an example of something, maybe going from 2 to 3 dimensions or something. Well, I don't know. I have difficulty with topology. It's a very tricky subject.
Oh, it's so full. It's one of my loves. I've got apart from having to finish my PhD in solar physics, I seem to be studying topology on the side.
Yeah.
So it's a beautiful topic. But I actually addressed this going from 2 dimensions to 1 dimensions in one of the notebooks. So we can jump to it now, or we can go in order.
Oh, carry on.
Phil, could I just ask you to warn me when an hour's up? I might lose, so I can just gauge how fast I should move. Okay, so that's what we hopefully will cover today. And I'm going to present some slides, and then we're going to jump into the notebook. So for the first notebook, it's clustering. You'll find the notebook should look like this. It says Notebook 1, clustering. And the spectra that we just looked at corresponds to a single point over here. So just imagine that each spectra is just a point in a multi-dimensional space. And what this algorithm does is it finds groups within your data, but I have to initiate how many groups I think the data should be clustered into. So it oscillates between a two-step procedure. One where, so here you go, I introduce centroids into this data space, these green points. All the points then connect to the closest centroid. And then the centroid updates itself to the average position of its cluster. And these little spiders crawl through your data space until they stop updating. And then the algorithm is said to have converged. In technical terms, they call this a vector quantization. And the point is that instead of now looking at all the little dots, we rather represent each group just with the centroid. So it's average position over there. So you see, we initiated 4 centroids, and k-means found 4 natural groups in the data set. I would have, if I had a group into 4, this is what I would have found. So you can think of the k-means algorithm actually as a multi-dimensional histogram, a dynamical multi-dimensional histogram. So in a histogram, what we do is we sacrifice complexity, or so we get rid of some complexity to make our results more interpretable. So if for instance, there's a bunch of numbers that exist between 75 and 80, but we go, okay, this difference is small, so we're going to just bin them all in the same bin. And this is precisely what k-means does. But k-means doesn't just do this for real numbers, it does it for more abstract quantities like shapes. So you can think of this algorithm like a histogram, which is quite sad, but that's basically what it does. It's very useful though. So this is what we can expect if we group our data, our spectral data with k-means. Over here, we initiate k-means with 3 centroids. It finds 3 groups. And as you can see over here, the centroids are dark, this dark point over here, and all the spectra in that group are overplotted. So these slight variations, we selecting to ignore them and just treat the centroids. So what does this do practically? Well, we go from millions of solar spectra to just a blueprint of 52 possible variants. So that's an amazing, very significant reduction. And now we can actually analyze this data. So what we did with IRIS is that we could automatically now see what the sun's emitting at different positions of a solar flare. So the yellow over here corresponds to these spectra. The black is on the flare ribbon, this energetic place. And the red over here, you can see it flowing down to the surface of the sun. So although this seems very simple, performing a vector quantization really allows us to start looking at the statistics on the sun.
Sorry to interrupt again.
Go ahead.
I'm not so familiar with these sophisticated techniques, but I am familiar with principal component analysis, which seems to do something similar. So what those do is they take the inner product of all these profiles and find a set of eigenvectors, and then you can sort of look at them in that fashion. So I was just wondering, I know that PCA is considered a machine learning, or at least something like that, algorithm, but I just wondered if you have an opinion about what the differences might be, and what the role of PCA might have been in trying to do this.
Sure. So PCA is, it's kind of like if you're a physicist, you kind of have these very simple examples. So, you know, like a chicken in a vacuum type scenario. So PCA is easy enough that we know exactly what's going on with the algorithm. So it's a great prototype. In terms of PCA, what you're doing is it's considered a dimensionality reduction technique. So we'll visit this, but as you said, you find the eigenvectors of the covariance matrix. You put them in an order. The ones with the largest eigenvalue then captures the most amount of variance in the data. What PCA is doing is that it's trying to preserve the global features of your data set. So we'll discuss this in that it really doesn't pick up any local features because it projects along a plane of maximum variance. So really, your local structure is mute. So I would not consider these two similar at all, because over here we're not getting rid of any of our dimensions. We in PCA okay, well you can keep putting these components together and figure out. You can start with very few and you get quite a noisy signal, and you put more and more and more, and you can reconstruct the spectra over here. But whether that finds groups, I don't think so. And if it does find groups, it will only be on a global perspective. And Phil, if I just get to that section that you're eager to get to, it will be much clearer because I've got a picture there. So
well, thank you. No, I just wanted to do that because many people will be familiar perhaps with PCA, but not with some of this stuff. So thanks for.
No problem. There's also a great equivalence between something more technical called an autoencoder, where it's a neural network. And if you've got, maybe you've heard the activation functions, if you've got a ReLU activation functions, and you basically force the network into a bottleneck and then back out, putting it into this bottleneck with these activation functions in one layer is mathematically equivalent. So the latent space over there is mathematically equivalent to performing PCA. So these technical networks, you can actually find a nice equivalence between the one with a particular setting and PCA. But yeah, we can chat about that later.
Thank
so
you
anyway,
so much.
Yeah, no problem. So this is K-means can also be used in another way entirely. So you can, it doesn't have to be the bread and butter, but it can be used under the hood in something more complex. And we used it to predict what different lines will be doing if we know what magnesium is. So Phil, maybe this is interesting for you, but if we've got a fixed magnesium profile over here, we can calculate the most probable output for carbon-2. And I think this might be useful for modeling purposes. But yeah, I don't want to give you the impression that because K-means is simple, it's not useful. In fact, it's quite the opposite. Because it's simple, we can interpret so much. So let's jump into the notebook quickly then. Now, let's see, I can't see my, whoop. I'm having an issue with my pointer. My mouse pad is gone. Okay, let me do this. Okay, so this is, we use K-means, and this is let me just see the time quickly. Okay, we got enough time. This is the publication that we put out. So there's some shameless presentation of our work over here. But it really was written by a first-year PhD student, so it might be the simplest version that you get. Here's the maths of the K-means algorithm. And this algorithm has been used, its citation, let's see, I think I put it here. It's been cited, here you go, a hell of a lot of times. And it's really impacted every single field. So it's not just specific to a single field. Here's the mathematics of it. In every single machine learning algorithm that I've come across, you've got something at the heart of it called a loss function. So in my opinion, maybe there's, there's some really fancy new things, generative models and so on. But in my opinion, the mathematics of machine learning is quite far behind physics and quite simple at the heart of it. There's a cost function, which you want to minimize. So you've got to put some thought and effort into this. And then you minimize this through one of the simplest processes, which is gradient descent, which is what we learn in first or second year. And so the loss function for k-means is called the intercluster distance. And we minimize that by iterating through a two-step procedure. So I went through this just a moment ago. And we'll see now with a different data set what k-means does with 4 centroids. So again, the thing to notice here is that the intercluster distance, this thing that we want to minimize, is the sum of all the red stuff. So you'll see that iterating between these two mathematical steps, the sum of these red lines actually decreases with each iteration. Now, something to point out with k-means is that it's actually a non-convex problem, which means that when we do this gradient descent, we're not guaranteed to find a global minimum. So it's common, you'll see in the code, to initiate k-means a number of times, and then look at the cost function when they converged for, let's say, all 10, and then just select the clustering with the lowest score. So we went from the maths to the maths in motion, and over here, it's the maths in code. So almost all of the code in these notebooks is from something called sklearn. They've done a great job they're mostly for unsupervised machine learning algorithms, but they've done a great job on making it really user-friendly and simple. This is great, but it's also dangerous that people just apply things, obviously. So I encourage you to read the documentation. Maybe I haven't even read it correctly, but over here, we're running k-means. This is a mini batch version. So instead of using the entire data set, we sample some data and we put our centroids in and update them. And then we take that data away and sample some new data and update on the new ones. So you've got this running sample and it drastically decreases the time for convergence. And it converges pretty much to the same results. So we can initiate the algorithm with a number of centroids, which we have to choose. Then we have the batch size, which we'll put into, let's say, a few thousand for our data set. And the number of times we want to initiate, because it's non-convex, we want to try and find a global minimum. So we're going to shoot this out 10 times and then select the lowest one. And this k-means plus, this is a special way to initiate the centroids. You can either just randomly place them on data points and go from there, but as it turns out, there's actually a really neat strategy of placing these points that most often lead to better solutions. So that's why there's this initiate command over here. And the output, we'll get let's see. So we get the centroids, the labels of the data. So each data point, which centroid it belongs to, the inertia. So all of the sum of all the red stuff, and the number of clusters.
Can I ask a stupid question again?
Go for it.
I'm really good. So if you can scroll up to your picture of the clusters that you just had. So this is a two-dimensional representation of something very interesting. What is behind all this? This is measuring the distance between the centroid and a data point, but that data point is what?
So the data point here is actually the full spectra. So if you imagine each wavelength that makes up the spectra, just form an orthogonal basis. Each one's just orthogonal to one another. And then these distances are the Euclidean distance between each single. So your whole spectral will be a single point in this. The wavelengths are 240 points. So it will be a single point in 240 dimensional space. And we take the Euclidean distance between the points.
Yeah, so the orthogonality seems important then. So how do you construct an orthogonal spectrum? Is that like a PCA kind of thing again, or is that something? I stepped out of the room, I got to confess, for a couple of minutes, but this is so interesting, I can't help asking.
No problem. I don't think, we're not assuming that that there's no correlation between the dimensions here. So I think it's safe to I've probably not thought about this enough, and I'm not sure that it's an issue, but it might be now that you pointed out.
I'm just trying to get a dumb physicist picture of what the hell is going on, because I think I understand mathematically what you're doing, and if it's not important, please do continue.
Well, I'm thinking whether it's a safe assumption. So what you might find interesting is that you don't have to use the Euclidean distance. In fact, if you use the L1 norm, so if you know your topology, the L1 norm tries to import the attributes of the real number line to higher dimensions. So for instance, a circle in L1 space is in fact a square. And there's some really nice properties that if these things are touching, they must share the same point and so on. So what you can actually play with here a lot is you can change your metric and see what happens there. And you actually get different tessellations. We use Euclidean norm because I said this is convex. And you can actually prove that with this norm, if you slightly change one of the positions of the point, it only results in a really small, insignificant shift of the centroid. So it's quite robust. But for the orthogonality thing, I'm sure it's safe. I'm sure I'm just not thinking straight. But imagine each point as all the lambda. So you've got all the lambda, 240 lambda points. And at each point, you've got an intensity, right? This makes your spectra. And just imagine this orthogonal 240 dimensional space. And along each dimension, you've got your intensity. And if you put this all together, you get one vector, and that's your single point. And so this is a two-dimensional representation of something much higher.
Okay. Yeah. Okay. Please don't let me disturb the flow anymore. It's I'm just intrigued by this whole thing.
No, it's great. I actually prefer conversation. So, okay, and the solutions exist, and hopefully I've written it out clear, so you can look at this later if we don't get through it. So now, just to try and understand how to interpret our data, we're going to look at how this algorithm behaves on something simple. That's a nice way to start. And then if we can find similar behavior, maybe we can infer what our data set looks like if we look back at the simpler data sets here. So I generate two data sets here. The one on the left is really well-defined groups. Everybody here can tell there's 5 distinct clusters. So I'd hope my algorithm finds 5 different groups. But on the right over here, our data could look like a blob. So we call this the blob data set. And it's not really clear. It's a really ill-defined problem now to find the correct number of groups. And remember, this algorithm requires one input from the user, and that's the number of centroids n cluster here. So the question here is there a way to automatically figure out what the most parsimonious group number is? Is there some method? So one method that exists is called the elbow method. And the idea is that we look at this intercluster distance, so the sum of all the red stuff once we've converged, but we do it iteratively whilst increasing the group number. So I start with one group, and you can imagine all this red connections here. And this is going to be a really large inertia. Then I add another group, and maybe the one group captures all of these and here, and we'll get a drop in the intercluster distance. And we add and add and add. And the hope is that at some point, we decrease really quickly, and then we hit this elbow where we decrease slower with the cost function. And this elbow point would indicate the most natural number of groups for the data set. So this is what we've just run here. And we see from the elbow technique, the intercluster distance really drops when we increase the number. When we hit 5, we get from really fast to just flat improvements. So in other words, we're adding more centroids within the same group. So we're really not getting much more gain than before. So, okay, this works for our first data set. And for the second one, you see there isn't really this elbow in this plot here. And that might indicates that we're actually dealing with a blob. So this is sort of like a fractal. If we're in here and we expand this out, well, we've got the same behavior over the entire space. So here's a little function that shows what the algorithm found. And indeed, if we initiate 5 groups like this technique tells us to, we get the perfect clustering for this data set. It's a really well-behaved data set. And over here, if we initiate with 5, well, again, we get this tessellated pattern, but who's to say that 10 wasn't a better option? So at the end of the day, this actually occurs quite often, and you need a scientist to actually have some personal say rather than just an algorithm. So there is a fair bit of human intervention if you get a data set like this. So let's now try this technique for real data from Iris. Just a heads up to my colleague in Zurich. He designed this library for Iris data, and specifically with machine learning in mind. And if you downloaded that big 9 GB file, you can play this. And this is the flare that we're going to be looking at. And what this library does is you can get an observation. It will produce what Iris saw on the GOES curve. So this is the X-ray curve. You can see the flare happens here when it jumps up, and it produces this image, and it spits out some data from the HEC database, as well as some dimensions of your data set and so on. So it's a really nifty tool. But anyway, so our data is coming from this observation and a quiet sun observation. So if we look at we can load our flare data set over here and the quiet sun data set. If we take a look at, there's a function over here that allows you to take a glance at the spectra in the flare data set. And that's what it looks like. And then each spectra has 6 features. So for instance, if I zoom in on this guy over here, we have a dictionary called, sorry, I'm jumping up and down. So we have quiet sun spectra and quiet sun features. This is, let's just quickly show you here. So let's look at the shape of this. So we've got thousands of spectra, and each spectra is 240 wavelength points. And for the features, let's do this, features.key, it's a dictionary. There you go. So there's 6 features. Let's look at intensity. Okay. Okay, and this has a dimension. So the intensity key for this dictionary produces intensities for every single one of the spectra in the quiet sun spectral data set, and the same for the flare data set. So that's what we're dealing with here. If we zoom in with one, these features are intensity, triplet emission, line width, line asymmetry, total continuum, and the ratio between these 2 peaks. You don't really have to know what that is, but just know that we're getting features from the spectrum. Okay, so here's the exercise session. You're welcome to try by yourself. I think we're going to run out of time. So I might just, Phil, maybe your advice would be useful. I can see I'm talking way too long here. So perhaps I should go over to the solutions part and we just keep going through, and then people can catch up and practice on their own time, maybe.
I would like to keep you going. I mean, this is really interesting, by the way, Brandon. Thank you so much. Keep going. Yeah.
Okay, so
yeah, Rajesh is not even not what do I mean? Rajesh is a computer scientist, so you've really got his attention here.
Okay.
And, I would love to see sort of a I would like to see a demo of what the outcome of all this is. I mean, just to see if you can identify with machine learning completely without any ambiguity what's so special about the flare profiles, what we might do next, all that kind of stuff. But
Okay.
I would definitely defer to others on the call, because I have a very specific kind of desire to understand flares, and this is really not about the specifics. It's really about the cross-disciplinary aspect. So I'd encourage others to pipe up if they want to see what's going on.
Okay, so thanks. Well, the options here are you can play around with the data set. This might take some time. We've got 4 notebooks to get to. So you can do that, and we might not visit everything, but you might then get some help and some hands-on experience. Or we can go through the material on the solution side, and you can revisit in your own time the version without solutions and try by yourself. So could I have some sort of?
I like the second option. I partook in one yesterday where the demonstrator went through a whole bunch of stuff by themselves, and then we were able to go and look real time, or we could go afterwards. So
okay.
I think if you can demonstrate how this works to us, I think that would be personally the most useful to me.
Okay, I'm just going to take that. If nobody's piping up, I'm going to take that and run with it. Okay, so let's just recalibrate ourselves here. We looked at a really simple data set, 2 data sets. We saw 2 behaviors. We're trying to figure out if there's a natural number for K. And we looked at this, this one method called the Albert technique. So we want to know if our flare data set looks like this or looks like a blob. Okay. So this is what we do over here. Firstly, we ran k-means on the spectra. We ran it with 50, you see over here, 50 groups. And literally, this is the command. And what I get out are my centroids. I get out the labels. So what each one of those black points, which green centroid they belong to. So this is just a list of numbers from 0 to 50, the inertia, so once it's converged, and the number of clusters we used, which is 50. And this is the output. So k-means finds, if I say 50, it finds 50 groups, and it says, these are the most natural groups I could find in the data set that you gave me. So you can see we've got some variation here. We've got some really weird looking profiles in spectra. And we've got single peak spectra. But if you notice here, this is something generic in machine learning. With our domain knowledge, we know that the intensity variable can vary hugely. So you can literally get spectra that are emitting just a little bit, or orders of magnitude higher than other spectra. So in this one feature, this intensity feature, what it will do in any machine learning algorithm is that because it spans such a large range in comparison to the separation between the peaks, which is a small variance, it will drown out all the other interesting information. So what you see is something called standardization. And for spectra, to enrich the data set, we actually normalize out the intensity. So in other words, we go to each spectra. This might be from 0 to 1,000. This might be 0 to 100. And we divide by the maximum so that each peak is from 0 to 1. Okay, so we basically integrated out the intensity component, and all features are on an equal setting with the same weight, more or less. And then we produce the k-means again, and we get a richer looking data set. So now we find a lot more shapes. If it's not apparent in this data set, trust me, if the data set's really big, not just for this toy example, normalizing will pull out a lot more interesting information than if you just ran it, because then your centroids are being used to get the same shape, but at different intensities. So maybe this is what you want, but we're actually more interested in the different shapes that the profile could take on. So the takeaway here is that normalizing or standardizing is a critical step in any algorithm, because it allows the computer to assign equal weight when it's performing its tasks.
So can I'm sorry again, I seem to be the pain in the neck here, but so the physics of the flare is that it is incredibly bright compared with anything else.
Yeah.
And what you're telling us here is to find features that include a flare. You're seeing more structure in those in which the actual brightness is sort of thrown away as a classifying tool. So for instance, number 10 here, I'm looking at your graph. Number 10 here has profiles that are familiar to me, and I've analyzed one particular data set in some detail with a paper published by Daniela Lacartos just a few years ago, in which we tried to explain those and extracted some physics from that. It looks like number 23. But then there are fascinating things like number 48, in which you suddenly see the photosphere at the bottom here. You see the absorption lines, which aren't present in almost any other thing. So I guess I'm thinking out loud here, but I mean, to me, this is astonishing to look at this thing. I mean, I don't know what to say. I mean, we were left with, you know, in the old days, taking spectra and saying, oh, this looks like a typical flare. Well, what the hell is a typical flare in this picture, you know? So clearly the machines are identifying something here that is, and also if you look at the line widths and whether those little peaks that turn out with the two strong lines that you see there in emission, whether, I mean, like half of these are in absorption in the core and half of them in emission. This is fascinating. I mean, this corresponds physically to different formation things, because I've spent half my life thinking about this stuff. I could spend another 50 years analyzing spectra between 0 and 24 here without even addressing the rest, you know. So I think what I'm taking from this is, you know, you're documenting the behavior of a natural system which is not yet understood in a fashion where there is reproducibility, there is a defined set of criteria you use specific algorithms which are you know, always going to produce the same result with different starting conditions. Obviously they won't, but with the same starting. And so what I'm looking at here is just an astoundingly rich data set for which applied mathematics is going to inform people like yourself in the future just the most absurd amount of new knowledge in this area of physics. I mean, this is totally revolutionary.
Exactly, Phil. I mean, this has occupied me for 4 years. So it's extremely rich technique for extracting.
I mean, Rajesh, what do you think of this?
So
stuff?
I'm actually, let me say a few things here. As I'm listening to this, I'm looking at another problem, completely different space, but exactly the same nature, and that's mass spectrometry. We rely on mass spectrometry for proteomics data, and for proteomics data, the molecules are too big, so you actually have to chop them up, and you basically get these mass spectrometer graphs, and those graphs come out unlabeled. And of course, generally speaking, in a lab, you know which molecules you're looking for, their presence and absence, and their titration from the mass spectrometry. But if I were to do what Brandon is doing, and this is something I was going to take it to our researchers there, and take 1 million of these mass spectrometer graphs, let's say. We have a farm that we're building up in mass spectrometry, and then find molecules that we were not even looking for. And I think that's where the nature of discovery will change. And of course, that's a very different domain. But I think the same idea here, you're looking for a phenomena, both emission and absorption, that is showing up in the way you cluster them, for example. But at the same time, your clustering can also lead to material discovery, especially when we talk about proteomics, where the cataloging is just impossible. It's impossibly big in terms of what you're looking for versus what you actually have in the sample. So yeah, so again, I'm a little bit superficial here simply because I don't know either of those areas in depth. But from the methods point of view, I mean, it's not very sophisticated what Brandon is applying, and it's pretty impressive.
Cool, thanks guys. So let's quickly, do you mind? I'm just going to grab my cell phone so I can keep track of time here. Let's just see if I speed up, you know why.
You have another hour. You have another hour, Brandon, don't worry.
Let's go then.
This is already a success, already a great success, your demo here, so.
Fantastic, pressure's off.
Yep.
So
just enjoy it.
So this is now what we did before, we now apply to our data set. So we had our toy model where we increased the group number and we wanted to see this shoulder technique. Well, we just repeat it again for the iris spectral data. And the point that I want to show you here is that we use completely two different data sets, 2-dimensional versus 240 spectral data. But the techniques are the same. So the point is you've got all this predefined machinery that's ready to go regardless of your data set, but with caution, of course. So this is what we find when we run the algorithm again with increasing group number. I plotted 3 plots here, 3 lines for each plot. The first one was the structured data set, which dropped off really quickly. Then we've got the blob data set over here, and then we've got our flare data set. And we can see that it appears to be more like the blob data set than anything else. And same for the quiet sun. So what we're looking at is, in other words, we could start from one spectrum and morph it continuously to another spectra. And basically, if we were living in this space, we could just flow between spectra. There's no super divide. This is what I take away from this information. So we're looking at a blob, which means that we've got to have humans to decide where the boundaries actually exist. That's why when you say there is downflow, but there's another one similar to it, it's because the algorithm had to choose a divide even if there wasn't a natural divide. You can look deep within each group and it's obvious that they're different, but when it comes to the border, it might you might need to apply some technical know-how. On a side note, K-means is an old and very good algorithm, but there are some other options here. So what you notice is that K-means says you're in this group or that group. So it's strictly binary. But you can also do a similar thing with an expectation maximization algorithm where you assign points percentage-wise to each group. So those occurring on a boundary are not thrown into this or that, but can actually have a percent between both of them. But you'll see that each one of these centroids, remember, has a full cluster around them. And we actually want to make sure that our centroids are good representatives of the data that they're representing. So over here, we just plot the spectra around it. And what you notice here is if your group number is too low, the variance in each group is too high. So let's say I only chose 50 where I should have had 80. If I have 80, this variance, this red stuff, will be much more tightly fitted to the centroid. So for instance, if you just go for your problem, throw in too few centroids without looking at the intercluster variance, you might actually be misrepresenting your data. So this is one way to make sure that you're not doing anything strange under the hood. And this is a fancy version to do it. I just provided a complex version and a simple version for you. And now you can select the group. Maybe we can do this for you. Let's go. So this is the actual real runtime. It's done. I will summarize it quickly. What k-means found. Okay. And now we can choose one. Let's look at 44. Okay, so I'll put 44 here. Okay. And we've got our output. So that's the end of this demo. And if you want to see the real results, this iris reader that my colleague created, it can load in the centroids found in this paper. And here you can plot them, and you can color code them, and then you can actually apply them to different flares. So this is what we did, and this is how we try to analyze this data. And just for an example, some really interesting spectra here, 11 and 12, which are colored in black, appear as black over here. And you'll see that they actually follow the ribbon front, this front of the right ribbon. So you can go through your data set like this and analyze patterns and try to figure out the physics in this way. But okay, so that's the end of this notebook. But now you might be asking, if we go back to the original, we're trying to figure out the number k over here. What's the best number of groups? Well, it's very simple over here because, well, we could just see it. So the question now is there a way to actually look at this very abstract data just in 2 dimensions? We're humans, so we need it in 2 dimensions. And this is the question that the next notebook tries to tackle. So in machine learning, there exists this bracket of techniques called dimensionality reduction that Phil was very interested in. And the idea here is that we're humans. We can only see in 3 or less dimensions, excluding color and all of this. So the problem is that almost all our data sets are multidimensional. Over here, they're 240 dimensions. If you're a string theorist, maybe you're used to 12 or 11, but that's an unreasonable number. So these techniques try to take the data from high dimensions, shove them down into 2 dimensions, and still try to preserve something about the topology. So just a question, if anybody wants to answer, you can. How would I fully characterize the geometry of this panel over here in A? So these 3 points over here, they exist in 2 dimensions. How would I characterize the geometry? Phil, if you're
Okay, I'm paying attention. I'm answering an email from your advisor, actually.
No problem. So anyway, you to characterize these points outside of a kernel, let's say, you would have a distance matrix, a pointwise distance matrix, right? So you've got 3 points. So then imagine a 3 by 3 matrix. It's symmetric, and the diagonal is all 0 because the distance from the point to itself, I, is nothing. So you've got a diagonal of 0, and then you've got the off diagonals will just be the distances between each points. So this 3 by 3 distance matrix has all of our geometry. Okay, so we're going to go through 3 different setups and see what happens in each case when we go from 2 dimensions into 1 dimension. Starting with these 3 points, I can embed them. It's called embedding, or and this 1 dimension is called a latent space sometimes. So this is the lingo. And from 2 dimensions, it's very easy to embed this in 1 dimension and keep all of the geometry. So the distance matrix over here is exactly identical to the one in 2 dimensions. And this is a very nice example because, well, this data, if you see, is occupying a subspace. So it's not making use of one of the dimensions. So we can just chop that off and perfectly preserve the geometry. And now let's change the data set. So now we've got this equilateral triangle of points existing in our 2-dimensional, higher dimensional space. And we want to put it in 1 dimension over here, this f dash. So the one way we can do this is to put all the points on top of each other. In a way, in 1 dimension, this is still an equilateral triangle, if everybody's okay with that abstraction. So if we look at the matrix, the pairwise distance matrix, the diagonal is always 0 because a distance from 1 point to itself is 0. But all the off-diagonal distances are equivalent. So imagine a matrix and then all 0 and all equivalent. Well, this guy has the same sort of setup, except everything's 0. So in a way, it doesn't violate it, it maintains the structure. So there's some topology that you can manage to carry over here. And now let's look at a third case where this is not possible and something has to break. So again, we've got in 2 dimensions, we have our equilateral triangle. And we have this extra point over here that really messes everything up. So we can try to preserve the pairwise distance matrix. Let's try and represent this properly. Okay, we know that to get an equilateral triangle, its topology, we can shove them all on top of each other, and this gives us the same thing. But now, no matter where we put this gray point, we're going to violate this matrix because this point is a different distance to every single point in the equilateral triangle. But in this setup, it's always going to be the same distance to all points. So we've shattered something here. Or we can try another option. Let's try and get these distances correct between the gray points and all the other points. But what happens then is we break the equilateral triangle. So the point is that this is most often the case. You cannot preserve everything when going from high dimension and shoving everything down into a lower dimension. At some point, you're going to have to make a compromise. And all these different methods compromise in different ways. So we're just going to look at 2 of them and what compromises they make. Here's a really colorful rainbow example. We've got this Swiss roll, and it looks like this in 3 dimensions. And in 2 dimensions, a good representation would be this. Because if you were, let's say, traveling along this line and was very big, to you, it will just look like this locally anyway. And again, embedding a half circle from high dimensional 3 space into 2 dimensions. So here is your PCA. And this is the first technique we look at. And what we're doing over here is we've got these blue points living in 2 dimensions. And we want to try and represent them in 1 dimension. And what PCA does is it tries to find the line to project the data on orthogonally. So what is the best orientation of this line? And PCA says the best orientation is when the variance, when the spread of these red points, when they projected onto the line, are maximum. So you'll see that when we get to 45 degrees going this direction. And that's PCA's first principal component. So it captures the most variance. So this is called the first principal component. The data varies most in this direction. So PCA projects everything diagonally, orthogonally down onto this diagonal. The second component is orthogonal to that, and it will be this guy over here. So we're going to try and use PCA on our flare data. Again, we put in our flare and quiet sun magnesium spectra. And we know that each spectra has different features. And let me just get something to drink. This is just a bit of technical work here. So some of these, the second technique that we're going to try is quite computationally expensive. I'm fortunate enough to have a lot of computer power on a server, but I would suggest drastically decreasing this number. So this will allow you to sample from our spectral data and not break your machine if you're running it locally. So we just get a sample of our data. That's what this code is doing. And then we've got this quiet sun and flare spectra, but for the purposes of this exercise, we're going to join these two together. And that's what this code block does. It just takes the spectra and concatenates it together and keeps track of which spectra comes from which group in case we need to color code it later. So now basically once we complete this block, we've got all of our spectra from the quiet sun and from the flares living together in this high dimensional space, and we want to crunch it down into 2 dimensions. So this is what PCA does for us. Again, the sklearn syntax is extremely simple. You'll see this pattern everywhere. We say the number of components that we want. So PCA components, well, it's 2. We're projecting it on in 2-dimensional space. If you wanted to go to 1, you can. And whiten is just an option that you do. You center all the data at 0. And once you call your model in sklearn, then you fit it and transform the data. So literally I said, okay, I want a PCA that goes down to 2 dimensions. It builds this model. You apply it to the data, and then you transform the data. And you get the spectra projected. So I've named it projected spectra. Then I can plot this projected spectra in 2 dimensions. And what you see here, we can color code them, because remember when I joined the data sets, I kept track of the quiet sun and the flare spectra, which is which. And the quiet sun exists here in this dot. And all the rest is flare spectra. So if somebody wants to guess why our data set looks so boring, you can guess now. Did I miss a step?
Not sure why. What's plotted? What does each point represent on this?
So this is again the spectra, but projected into 2 dimensions using PCA. And the orange spectra are from flares, and the blue spectra are from the quiet sun.
So are these the eigenvalues of the?
These axes are the eigenvalues, first and second principal components.
Okay.
So what for everybody else above, we projected onto 1 line, but you can go for many dimensions and put the first and second component together. And from these 2 components, you can make a plane. So basically, we've got all these points living in high space, and we take a plane and we figure out, okay, this is the best angle, and we scoop everything up like so, and basically like running the data into a window. And this is what we see. And the question here is why the quiet sun seems to be drowned out here. I really don't see any structure there, right? It's just a single blue point in the corner. So the answer here is before, we didn't normalize the data in the steps before. So if I apply a heat map in this code block with intensity, I can see that the spread is actually caused by intensity. So the quiet sun is low intensity, blue, and then all this is flare, high intensity. So again, I standardize and normalize my data set, and this is what comes out once I've normalized. So now I can see the flare spectra in orange and the quiet sun spectra in 2 dimensions. So the first thing that we learn is it's really not a difficult job to separate these 2 classes. So if you want to build an algorithm to tell you whether you're looking at the quiet sun or flare, all you have to do is get something that makes a line through the space. So looking at the data in this way will tell you these 2 data sets are really easily distinguishable. And You don't have to expend massive amounts of resources to separate them. You can really do it with a really simple model. So what we can do now is so if you remember over here, the flare spectra is up on the left and the quiet sun is here, the blue. And we can project all of our features over this very easily. You see that the flare spectra are more intense. I think you can clip the color map, so you can change the clipping over here. The line width, it seems like the quiet sun has quite broad lines, but this might be downflow in the flares over here. The total continuum, because they're normalized, the quiet sun has the continuum up high. When it flares, the peaks really outclass the continuum emission. So when it's normalized, the continuum almost looks flat, which explains the total continuum emission. And then the KH ratio, if I didn't get this wrong, the flare spectra seems to be optically much thinner than the quiet sun spectra. But I must check that I didn't switch this around. So the takeaway point here is that you can actually use PCA to visually explore your data set and make decisions of things down the line in your pipeline. For instance, you wouldn't want to apply something fantastically complicated to separate these two classes.
So
and,
what fraction of your variance in the PCA analysis is contained in the first two eigenvalues?
Actually, a lot. So a lot.
Yeah. So you don't have much information. You only need two pieces of information then to characterize a flare.
Yeah, exactly. So exactly, that's exactly right. Wow. To characterize a flare, but Phil, you know that the devil's in the details with the spectra. So what we're losing with PCA are all these small variations that are only picked up by eigenvalues way down the line, eigenvectors down the line. So yeah, but for this task, just two components, and then you can figure out what these are. But here's the problem with PCA that you can now visualize. So let's say we've got data living in this blue point here, okay? Many data points. And you've got data over here, data over here, data over here. So we've got four groups of data, and now we do a PCA. Well, PCA looks at this, the variance of the data, and it says, wow, this delta D separating these two clusters is much bigger than the delta D separating these two clusters. So naturally, the PCA solution is this guy. And when you project orthogonally down, you lose all of this local structure. So that's the problem with PCA, is it's a global algorithm. It does great in capturing the distance between global attributes, but it really does trash when it comes down to the fine detail. So the next technique is fantastic. I love the maths behind this, is beautiful. But the next technique allows us to probe the structure of your data set at all length scales. You can actually, there's a little knob that you can twist, and you can look at the local structure to the global structure. So I hope you make use of this tool, but don't get carried away with it. It produces fantastically beautiful results. The extent of which these results are useful, maybe don't push it too far, but I've had fun with this algorithm, and you can use it for interpreting your results. So how does this differ from PCA? Let's look at the intuition. You can find a description of the maths in a paper that I wrote over here, and the original paper for the method is actually very, very clear. So I will suggest this. And there's this link over here that you should definitely play with. It's like a video game. It's fantastic. It teaches you how to interpret the results from this method by allowing you to interact with data and so on. So let's go back to an example, a simple example. We've got data living in 2 dimensions. This is F2 and F1 are our basis. And we've got two clusters here. We've got these black points, and we've got these other data points, these gray data points. So the first step that this algorithm does is, instead of using Euclidean distance, it uses something called statistical distances, which isn't too scary, but we place Gaussians on top of each point, and then we measure the distance between 2 points by the overlap of their Gaussians. So stop me if I lose you. Imagine your space of points, and above each one is living a Gaussian distribution. And now, instead of using Euclidean distance to define our distance matrix, this is just a matrix over here with values in it. Again, the diagonal is all 0 because the point's distance to itself is 0. And now the distance between the points is this blue overlap. So xi and xj would be the overlap between these two Gaussians, no longer the Euclidean distance. So we find with this concept, we can build up this statistical distance matrix between each point. So over here, it's a 6 by 6 matrix. Now, the next step here is the tricky one. It's called entropy or information entropy. It's very similar to entropy in physics, sometimes also called Shannon entropy. And the entropy is set by one value called the perplexity. So what happens is that I choose a entropy for my system, and then the Gaussians adapt themselves such that this entropy is maintained. So in information theory, entropy is the amount of surprise in a distribution. So if I've got a Dirac delta function, this is 0 entropy because I know exactly the result. If I've got a really broad Gaussian, let's say so broad that it's flat, then my entropy is at a maximum, my information entropy, because I don't know what my result's going to be. This is the worst possible outcome. So if you look at this image over here, the Gaussians living above each point actually have different variances. And that's because we go, I want this information entropy to be X, and then the Gaussians locally adjust themselves according to the density of points underneath them. So this is actually the heart of this algorithm. So once we choose this entropy, we get the Gaussians adjusting, and we can form this matrix. Now we want to reproduce this in one dimension. So what we first do is we randomly throw our points into one dimension. And then again, we take statistical distances. We use a t distribution, student's t, instead of a Gaussian for reasons that you can read about. And we can build up a matrix again. But because we just threw the points there, this matrix isn't going to look anything like this matrix over here. So what we do is we measure something called the Kl divergence. So we can tell the difference between this guy and this guy by using this statistical distance measure. So if you think of this matrix over here, I hope it's not, I hope I haven't lost everybody. I think I'm doing a terrible job at explaining this. But if you look at this matrix here, you can imagine a distribution living over it in 3 dimensions. And the Kl divergence tells you how similar these distributions are. And what you want to do is minimize the Kl divergence. And you do that once again by gradient descent, a very simple algorithm. So this is what this algorithm does. And by adjusting the entropy, we can look at the global data, the global structure, or the small structure. So let's see what we get when we apply it to our data set. Here you go. So the orange points are the flare spectra in 2 dimensions, and the blue points are the quiet sun. And at perplexity 1, so this means just the local structure, all the way to more global structure at entropy of 450. So when we have an entropy that's far too low, these Gaussians are basically, these points are floating around. They can't even sense that there's other points around it because the Gaussians don't overlap with anything. So you get this very free-flowing constellation of points over here. And as you allow these Gaussians to grow, they have to preserve more and more of the structure around them. So really, we're looking at the local structure over here, and we souping it up to the global structure. And you can get a lot of topological information like this. For instance, I've come across data sets where you can clearly see that one data set's living within another one. So you've got this enclosure sort of property, topological property that you can identify. And yeah, it's absolutely beautiful outputs and very organic. So one thing to notice about this algorithm is that it's like PCA, you get a mapping and then you can bring new points and just do the transformation. With t-SNE, it's completely organic. The end result depends on every single point. So I can't take a new data point, a new spectra, and figure out where it maps over here, because it actually evolves in the dance. And it's kind of like you can go into the mathematics and it equates to a system of springs interacting with each other, forming the shape. So it's very, very pretty. And again, just like with PCA, we can plot our features over. So here's the quiet sun is in this cluster, completely separated by t-SNE. So t-SNE has zero problem distinguishing between the two data sets. Here's the flare are living all here, and the quiet sun all here. It's fantastic. And you can see the total continuum, this big piece in the middle of the spectra is really dominant for quiet sun. But for flares, remember, the peaks dominate so much that the ratio is far lower. So this continuum is more or less flat for the flaring spectra. The triplet intensity is really high for flares and non-existent for quiet sun. KH ratio, you could, so full, you were asking, you just need a few components. Well, yeah, why not just take the KH ratio and the total continuum, and it seems to separate them perfectly. So there's a lot of insights you can get, and it's really pretty. And one more note is that it's not just for aesthetics, but dimensionality reduction is actually used in a follow-up to more complex algorithms. So you often want to generate a smaller input that's extremely informative and has got rid of all the garbage before you feed it to higher order algorithms. So dimensionality reduction can find all the good stuff and then go from there. So it's also useful in this upstreaming task. Okay. Next topic, if anybody's got questions, you can ask, and then I'll drink something quick.
I mean, the beauty of the abstraction into mathematics is incredibly, what's the word, seductive. To me, it seems like you can go into such things as topology, maybe even group theory. I don't know what symmetries there are and stuff, but there's just a natural kind of, for me, it's an attraction to want to understand things in terms of elementary mathematics. Some of this stuff is not elementary, obviously, but it is nevertheless mathematics in the sense of, you know, topology and whatever you've got going on here. And I can't help feeling this is really gonna, this kind of penetrative understanding of what's going on behind the scenes and visualization in terms of what we understand in terms of projections into various dimensions and stuff has got to be absolutely critical. And surely this has produced astonishing results in other fields. I mean, I am just so ignorant of this. I'm just so fascinated to see in a relatively simple system like the sun and its flaring and stuff. I mean, compared that with a response of a human body to you know, a COVID or any other virus, this is a much simpler problem. And I mean, I just can't help feeling that science is sort of almost just beginning as a result of this kind of stuff. Maybe I'm just not understanding what's going on, but I am so impressed with what this stuff is all about. I'm gonna have to view these all over again, all these, many of these demos this week.
It's really beautiful, and anybody interested. So with Lutz, I always try to hide my research questions in such a way that I can actually learn some maths. So I've got to sell the point to her, but it's really pretty stuff. And if anybody's interested in a cutting edge dimensionality reduction technique, there's one called UMAP. The paper is really hard to penetrate. It's topology at a level that I wasn't trained for. So simplexes, and it's producing really phenomenal results. So UMAP, you should take a look at this. It might be the next one.
So Brandon, this stochastic neighborhood embedding, that is coming from your group because of this
is not from our group. This is just an application from another group.
I see. Okay.
But it's quite a recent development, and UMAP is just a few years ago. Yeah.
Well, it's very intuitive, so I was pretty impressed that, you know, going from Euclidean distance to actually just looking at distributions and looking at their overlaps. To Philip's point, really, you know, it's almost like building a new instrument to look at the sun, and that's what your computational analysis is doing. Is you still need to understand what you're looking at, but it's giving you a new instrumentality into the physical world, and hopefully to the living as well.
Yeah, that's a great insight. I think it's been said before that you know, Aristotle built his telescope to see into the physics, and this has been equated to, you know, the next generation's telescope, in that when our objects are big data, this is our new telescope. So it's a nice equivalence there.
I have one question here. For choosing the number of components in the principal component analysis, how do you decide that, okay, 2 are enough and maybe you don't need third component or something like that?
This is a decision that's left up to you, because basically you degrading your data, and you need to set a limit that you're comfortable with. So it depends completely on your task at hand. You would like to get to the point where it's still usable and it's very quick for whatever you want to run, without any of the extra baggage. But with this methodology, PCA, you can actually very easily see how much each component captures in terms of variance. And you can, within the first few components with some data sets, you're almost at 99% of the data's variance. So you can monitor the first principal component catches 90, the next catches 5% of the variance, the next 2, and so on. And then it's personal preference with the data that you're using. So there's no one answer, but you can see how much variance you're capturing. Yeah.
Yeah.
Okay. For the next topic, these are all techniques that can be used with any data set. In our group, it was important. This was actually one of my first tasks, was to find really funny stuff. We've got huge data sets, but how do we find the anomalies? Because it's generally the anomalies that that actually lead to paradigm shifts. So is there something really neat that can find these anomalies for us? We don't want to see the same stuff all the time. So the technique I'm going to show you here shortcuts a general problem with outlier detection. The problem with detecting outliers is that it's normally done from this direction. you figure out what normal is, then you try to look.
Brandon, can you increase your screen size? It's very narrow. I can't read. Yeah, I think that's.
Is that fine? Little more?
Better.
Okay.
Yeah, that's good.
Great. So here's the pitfall with most outlier detections. This is a small notebook, so I'll capture your attention quickly and then we're done. But it's really neat. It's worth listening to. Again, a beautiful little trick here. So most methods focus on what's normal, and then they define outlier from how far away that point is from what's considered normal. Now, the problem is to build a model of what normal means requires a lot of data. So if I've got a massive data set, the algorithm that I'm using for my outliers in this normal flow has to look at a huge amount of data, which is computationally sometimes unfeasible, build up distributions, find out where this distribution is thin, and then assign an outlier. And that's a lot of work. So what this technique does is it says, no, let's actually start with the outliers and not try to figure out what's normal at all. And it's really elegant. So here's it explained in terms of pictures. You've got your data points, again, these circles. They could represent our spectrum or any data. And you've got the blue point over here that's more or less normal. It's surrounded by lots of points. It's not an outlier. Over here, same data set. You've got a point living far away from all the other points, correct? So this is an outlier. Now what this algorithm does is two things. It does them randomly. The first thing, it chooses a dimension, either X or Y, this direction or this. Okay, let's say it chooses the Y-axis. That's one random choice. The next choice is where on this axis should I intercept with a line. Okay, it chooses here randomly, and it draws a line. And it keeps doing these two random things. Axis, where should I draw it? Axis, where should I draw the line? So what the algorithm does is it populates the space with these lines. And this is called building a tree. So growing a tree. We grow a tree through this data space. And now what you'll notice that's very obvious is that the outliers are statistically isolated much earlier than the normal points. And what we mean by isolation is that with this random process, at some point, we're going to get a point just living by itself in a subset over here, this little square. So it's isolated. And a normal point, on average, is going to take many of these divisions. Okay, so in other words, the number of lines that have to be drawn until a point gets isolated is indirectly proportional to how much of an outlier it is. And if you're familiar with graph theory, this is the construction of a binary search tree. So every time we separate the data, we go from the data sets at the node into two subsets. And then we split it again. And basically you grow this tree, that's why this tree analogy, until each point arrives on the leaves and is isolated. So this would be on the leaf. And why is this advantageous to us? Well, now we don't have to even look what normal is. All we have to do is feel the very top of the data set, and we capture all the outliers without having to run super heavy algorithms, building models of what normal is and what isn't. It's really just a simple two random step process. And now the problem is that it might be possible just by chance to isolate a normal point first before isolating an outlier. You can think that the first two random choices are these two lines and this one, and then we isolate a point here in the middle. But on average, this won't happen. So we assign a point as an outlier or an inlier by growing many trees and then taking the average value of the number of divisions needed to isolate the point. So this is what you see over here. We have this blue spectra, that's more or less normal, and this outlier, that's got all of this noise on it. Maybe Phil is interested in that. I don't know, metallic lines or what that is. But it's really an outlier for sure. So what we do here is we go, okay, let's grow one tree, and we keep growing trees to 100, and we see that the outlier score for isolation forest captures this guy perfectly, but it jumps around a bit and then converges. And that's because in the beginning, if you just grow one tree, just by chance, you might get this wrong. But statistically speaking, if you grow 100 trees, you're going to isolate this guy much more often early on than a normal point. So the point is you can truncate this process, not go everywhere, and this huge data set, you can find all the outliers with minimal computational expense. So that's the point of this method, and it's just really elegant in my opinion. And I constructed this sort of diabolical data set to prove a point here. You can see this data over here. There's an outlier. It's living over here, right in the middle. This is an outlier, but what's interesting here is that it's also the most average point. If I sum everything up, it's going to give me this point. So this can often fool many algorithms. I try one technique over here. The technique goes, okay, let me see which ones are outliers. And it colors all the outliers orange. And it completely misses the one that's obviously the outlier in the middle. And with much less computation, isolation forest picks this guy up immediately. And not only that, if you look at what it scores it as an absolute outlier, not just maybe it's an outlier. It's an outlier by far. So this notebook, again, uses the same data sets and the same tricks. And we use the quiet sun spectra for this data, and we take one flare spectra and join it to the data set. And we ask isolation forest to find the outlier, and it says, yes, it's definitely the flare spectra. And we grow the trees and see that it converges to a stable outlier score. So that's a neat little technique that I think might be useful for any data set. And I'm running out of time here. Maybe I can give it a try for this.
Well, can I want to make one observation, if I might, for you and the rest of the group. I mean, I have to say, there's a philosophical understanding that you seem to present towards science, which I think is really profound. I mean, I've been taking notes here, and you say generally the anomalies, it's the anomalies that lead to paradigm shifts, and so you found a way, you've actually found a way to do the most important work in science, which if you read Thomas Kuhn's book on scientific revolutions, which I know is a historical study, and I know it's debated about what it means and what have you. Philosophy never gets you anywhere, I don't think, but it's fun to do. But even aside from all that, if you take that with an essence of truth, this is a way to avoid doing incremental research, which unfortunately I think has clogging up the arteries of modern institutional science to a large degree. Yeah. I know I'm making grandiose statements here because part of my job is to make grandiose statements tomorrow morning. So I'm just trying them out.
You're warming up.
I'm just, what I'm saying is I really appreciate that you've acknowledged that there's a philosophical and methodological choice you've made towards looking at science in a way which perhaps is more productive than other people's, and I'm excited by this. I got to say, this is an unusual perspective. I think it's shared implicitly by many of the best people in solar terrestrial physics, Gene Parker, and then you go to, I mean, I can just list a whole bunch of people that really thought carefully about these things. But I think what you've done here is you've sort of identified a methodology by which you can arrive at interesting new results in a fashion which is consistent with the scientific methodology that is most productive. That isn't a remarkable achievement. I got to say this. And it's not just because I've had a glass of wine either. I think this is, I think this is extremely, extremely important. And so if you don't mind, I'm going to mention this tomorrow morning when I summarize up where we've got so far.
Please go for it. Thanks, Phil. It's nice feedback. So now that's my favorite topic is last. I don't think we're going to have time. We don't think we're going to have time for this. But so I can zoom in here and see how far we get, if that's okay with everybody. So very often you want to measure the correlation between two random variables, okay? And I want to demonstrate to you that using covariance is maybe a poor choice. So what you have over here is the WHO data set, okay? So each point over here represents a different scatter plot, and we sample 3 different scatter plots that you can see on the right. And I want to argue that this quantity in information theory called mutual information is much more better metric than the covariance score. So if I take a data set over here, you can see that there is no correlation in this data set whatsoever. Great. And accordingly, it scored a low covariance on the y-axis and a low mutual information on the x-axis. So both metrics get this right. For this data set, there's a strong linear correlation. And this is again picked up with a high mutual information and a high covariance score. But now what about this distribution? There's clearly a trend in the data set. The variables are connected to each other, but it's not linear. And covariance actually doesn't pick this up. It scores it very low, but it's completely picked up by the mutual information. So the point is that if I'm looking at something complex like spectra, where all the little bits and bobs can vary at different speeds, at different times, in a number of complex ways, there might be a connection between all of these features that cannot be captured by covariance. So we need to measure the mutual information, which picks up both the linear and nonlinear correlations. And this is, again, a super elegant method for doing this. And it uses a neural network. So the mutual information is given by this equation here. It's the logarithmic distance between something called the joint probability distribution and the product of the marginals. So the probability of the marginals means what's the probability that my x variable is so-and-so, and what's the probability that my y variable is this. And then the joint is what's the probability that they occur together. And if you see, if I multiply these two together, I think in an outer product, if I remember my mathematics, I form a distribution that would be the distribution to expect in the denominator here if the two variables were completely independent. And the guy on the top is what they actually are. So if you take the logarithm divided by, so it's this minus that, it's actually measuring the Kl divergence, the distance between what I would expect when it's random versus what it actually is. So the difference between these two distributions tells you how well correlated they are, linearly and non-linearly. So it captures everything. So we know what we want to measure. How do we do it? This is the network that we use. It's slightly complicated. Well, maybe not for some people, but for me initially it was. So I'm going to quickly scoot over here and start up. So we want to calculate this. We use something called a mutual information neural estimator. Now, the beauty of this is not in the architecture of the network, but it's in how you sample the data. So let me break this into steps. We taking information, data, spectral data from the sun in 2 different pixels. We're sourcing it from 2 different pixels. In the top part of this network, we want to see whether a magnesium line is correlated to the carbon line, let's say. So we take the magnesium from the same pixel that we take the carbon. So we source it from the same pixel and we feed it into our network. The network then compresses this high-dimensional raw spectral data and maps it into a single real number by this blue point over here. And we don't impose any restrictions on the network. We don't tell the network how to do this mapping from high dimension just to one real number. We tell it can do it however it wants. In the bottom part of this network, we do the exact same procedure, but now we take our spectra from 2 different pixels and we feed it into the network, we concatenate and compress it down to a single real number. And together, we ask the network basically to distinguish between the upper and the lower channel. And here's the trick. The lower channel is sampling from the product of the marginals. So it's taking its 2 lines from 2 points that are supposed to be uncorrelated. In other words, the only way that this network can try to distinguish between the lower and upper channel is to learn all of the correlations that exist within the same pixel between the 2 spectral lines. And basically, if the network can pull these points apart, the further they can pull these real numbers apart, the more mutual information exists between the data. So it can actually be shown mathematically that this forms a tight lower bound on the actual mutual information. We then created this neural network, and we wanted to see how magnesium was correlated to carbon, how carbon to silicon, and so on. And we literally fed in all of our FLAIR data, and we generated these matrices showing the mutual information between the lines. And they what we expected. The magnesium and carbon have the highest mutual information. They have similar formation height, similar atomic physics. A low score was given to iron 2 and a transition region line. So it all matches up with expectation. And we could actually see how the solar atmosphere is coupled and connected during a flare. And it becomes, these lines share more information with one another when there's more energy being dissipated in the atmosphere. This is the GOES curve and tells you how much energy is coming into the solar atmosphere. And all the mutual information peaks when this curve peaks. And we can actually pinpoint the locations that are most connected in the atmosphere on the slit jaw images of Iris. And we see that on the flare ribbons, we've got most correlation between these spectral lines. So that's what the method does. I could go on and on about this, but there's just not going to be enough time. In this notebook, you can run through. So this is the only one that's written in PyTorch, so it's not the sklearn. The syntax of PyTorch is extremely, if you know Python, you'll be at home with this syntax. It's very Pythonic. So we create a network here. This is the whole network. This is the structure of the network and how we want the information to flow through it. And then we can train the network on our 2 spectral lines. And we can see what it guesses the mutual information is. Well, it doesn't guess, it actually gets it right. So mutual information between magnesium and carbon much higher than magnesium and iron 2. And the questions over here that I asked you to perform is to not compare different spectral lines, but to see which features are correlated to one another. So hopefully you can play with this code and get this output over here. And we see that for magnesium, the intensity of the triplets is really well correlated to the line core intensities, and we go down in correlations between features. So it's a great toy. It can literally compare anything, but it's super adaptable. You can feed images in the top, and you can feed spectra in the bottom and see the mutual information. So I really recommend that you try to use this in your research. Yeah, thank you. That's all for me. I think we're about done.
Well, thank you.
Yes, thank you. I mean,
Thank you.
Is King Fai, are you the one that was monitoring this for us in this meeting? I can't remember which of us was assigned to kind of handle the questions.
Rahish was actually assigned to handle
Actually,
the
I was
questions.
assigned, yeah. But
Well,
I'm looking at the questions. Sorry, there was one question about number of principal components. I think you answered that question, or did you? From Abhay Karnataki, that how do you choose the number of principal components in your analysis?
Yeah. So we said that you can look at how much variance each principal component captures, and then it's a decision down to the data sets and what you're comfortable with throwing away. So there's no one answer. Yeah.
Yeah, and I think in this case also you have a kind of criteria that quiet sun and active sun regions. So the 2 dimensions could be quite enough, I think.
Sorry, 2 dimensions could be?
Because we have a quiet sun region and an active sun region. So does that kind of translate to having 2 dimensions for the data analysis?
I don't think so. Not really. No. The dimensionality would not be just because of the classes. I think I could have spectra from a sunspot, from a flare, and from a quiet sun. And I would imagine that I could also put it into, actually I've done it, you can put it into 2 dimensions and separate it very easily. So it's not because we just sampling from 2 regions that we can compress it down. It's got to do with something deeper, I think, than that, the actual shapes of the spectra.
Okay.
I am so interested in this stuff. So many things occurred to me. I don't even quite know where to begin, but I'm really struck that it seems as if this mutual information thing, which looks like to me, to a physicist, like a modified kind of entropy, you know, and I understand entropy is not really a physical idea. It's really sort of more a mathematical one in terms of information content and what have you.
It's just numbers. Yeah.
yeah, and it's you know, I mean, but from the point of view of a numbskull, not numbskull, but an experienced physicist, I have to say that I think this mutual information thing and the idea that you've actually espoused in much of this, or at least that I took from it, was that this is almost. This is the ideas you presented. Some of them are central to how we decide which kind of data to include in a machine learning process as input and output. I mean, the idea that what I'm kind of thinking about in my head is that there's a metric that you're using here, like the information, as opposed to the covariance and what have you, that seems to entail, when it spits it out, it's entailing a much more informative expression of what's going on in the data that you have, no matter what the form is. And so I think these ideas can be applied, for instance, to let's imagine you're a NASA manager. What actual information, say you have a classifying machine learning algorithm that says I'm either going to flare or I'm not. How do you decide what other information you want to feed into that thing in order for it to work? And for me, when I listen to what you've presented, there is something to be learned from models and perhaps the existing observations that we have that would enable us to address that problem. Whereas in the past, it's always been a sort of scientist sort of proposing something and, well, why don't we observe this part of the magnetic field instead of that one and see how it improves it? This stuff seems to be offering a way, if I'm understanding it right, in which, given a modest amount of data, either from an experiment, a numerical experiment, or from a real experiment, in which to decide what's the angular resolution we need, what's the spectral resolution we need to propagate information into answering the question that we want in a very general sense. I hope I'm making sense here, because I'm thrilled to witness what I think is the beginning of a real change in the paradigms in which we're going to be operating. And I hadn't really understood this. I took it on face value from people like Rajesh and others that are on the call here, and that this was going to happen. But I'm starting to really see this now as a physicist. And I got to say, I'm glad I'm retiring soon, because you're going to have a lot of talent to really handle this stuff. I mean, your understanding of the pure mathematics, and but not just that, it's the understanding that it's relevant to what we're doing here, topology, these kind of concepts. These are not easy things that people most normally deal with. But I've got to say, this is a really exciting era to see, and I'm going to try and portray that in the morning when I summarize a few things here. I hope that Rajesh agrees, and I hope you agree.
I do agree. I actually could add many more things, but here is a question from Anka Marginian. For the network from the notebook 4, how is the label computed? I don't know if you have it immediately.
How's the label computed?
Yeah, on the network, on the notebook 4.
So maybe you unmute yourself, and then we have a discussion. What do you mean by what do you mean by label?
Let me see if Anka. No, Anka is there.
So Anka, in this case, maybe.
Yes. Hello. Very interesting. I really liked your presentation. So I didn't quite get how you compute the output that the network should have.
Okay.
I mean, the choice for the input I understood. Very nice idea, but I didn't get how you compute that maximum.
You don't want
difference.
You don't want to put any limit on it. So what's probably confusing is that a normal neural network has, you know, an output target. With this network, you don't want to constrain what the output will be. If you see in the code, there's no softmax applied to the last layer. We're literally trying to get the blue and the orange point as far away from each other as possible. And if the network can't tell the difference between sourcing from the product of the marginals or the joint distribution, it literally can't move them away. They will fall on top of each other. Because one thing to note here is that the parameters are shared in this network. It's not that we've got autoencoder 1, 2, 3, 4, 5, 6.
Yeah, I understood that. But in that case, how do you compute the loss?
So the loss function, if you see this guy over here, this mutual information, there exists something called a dual representation. This allows us to rewrite the mutual information in terms of both distributions, not just the joint distribution. And we can then parameterize that as the supremum. So we can I encourage you just to go and look in the literature. There exists a dual representation of this equation, and it allows us to parameterize it in terms of a neural network, and then we can actually take the supremum of the weights of the network to calculate the mutual information. And you can go step by step. So our loss function looks like this in the end. Here it is in code. It's in this code block over here. And yeah, it's a bit technical to go into, but read the paper and you can see how they go from the first equation to this dual representation.
Okay, thank you. Thank you. All the material were very, very nice and interesting. Thank you very much.
Thanks for the feedback.
So we are over time, but I just wanted to say maybe 30 seconds rejoinder to Philip's point. The world we see through observables and observation phenomena.
Everyone, that's 20 seconds. That's awesome. So, yeah, that's done.
Yeah, we are done. I think so. I think with these new models, there is a rise of non-parametric
The breakout
methods.
sessions went as well.
Yeah, so,
It was really breakdown.
okay, let's do that.
So thank you everybody for
There
listening
was
to me talk 2
scrambling
hours.
for me happening.
It was
in
amazing to
the
have a
crowd.
captured
The
audience.
room decided it was not.
Thank you, Brandon. We appreciate that.
Thank you, everybody.
It took a long time for us to log in, but once we were in, it was fine. So, yeah, I was worried.